Hi guys, welcome to Lesson 7 SN Part B, Operations with Scientific Notation. Our objective for today is that I can multiply and divide using scientific notation. So our essential understanding, same as yesterday or similar as yesterday, scientific notation is used to represent very large or very small numbers in a more manageable way, and we can use these numbers to perform calculations. So problem A, multiplying with scientific notation. Now this comes from the textbook, section 7.2, problem number 3. So when entering, I'll get to that little tip in a moment. So there are two ways that we can multiply numbers in scientific notation. We can use our exponent rules and multiply the different pieces, and so do 3.4 times 2, and then 10 to the 5th times 10 to the 4th. So 3.4 times 2 would be 6.8. 10 to the 5th, 10 to the 4th, how many 10s do we have? This is times 10 to the 9th power. All right, that's one way of doing it. The second way is what I allude to in our calculator here, or our directions. And I said when entering it into the calculator, use the EE button to represent times 10 to the. So, if we have our calculator here, we've got 3.4. We use the second and the caret to give us the little e, and we put our exponent, 5. The e represents times 10 to the. So 3.4e5 is 3.4 times 10 to the 5th. We multiply that times 2 times 10 to the 4th. And our calculator gave us our number in standard form, not exponential or scientific. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. 6.8 times 10 to the 9th. Okay. Now, one thing you can do when we're dealing with scientific notation, if you go to your mode, most of you should be set on normal. If you switch it over to scientific and quit, and you do the same problem, you'll get it in scientific notation. 6.8 times 10 to the 9th. All right. Now, letter B, 8.8 times 10 to the negative second times 5 times 10 to the second. And we need to figure out what that's going to be in scientific notation. Now, if we multiply 8.8 times 40, or times, 5, we're going to get 44, which is not quite what we're looking for here. So we need to use scientific notation to get this done. Now, 8.8 times 10 to the negative second, so we type it in, 8.8 times 10 to the negative second times 5 times 10 to the second, that's going to be 44. Or if we want to write that in scientific notation, it'll be 4.4 times 10 to the first power. So not a super great example there of where you need to use scientific notation. You can see much easier to just write 44 than this one in scientific notation. But when we saw the calculator, this was 6, 8, and then 8 zeros following it. Much easier to write it, 6.8 times 10 to the 9th. All right, I want you guys to try letters C and D on your own, and I will go over the answers. So I'm going to use my calculator for these. So I type in 4.56 times 10 to the third times 1.2 times 10 to the negative second, and we get 54.72. I'm not going to bother writing that in scientific notation because, All right, my next problem, we've got 1.02 times 10 to the negative 6th. So we type in 1.02 times 10 to the negative 6th times 2.99 times 10 to the negative 3rd. And we get an answer of 3.0498. 3.0498 e negative 9 times 10 to the negative 9th. I never, ever, ever want to see you write the letter E in your answer. If you write 3.0498 e negative 9 in your answer on a quiz or a test, it is wrong. Period. This is scientific notation. This is calculator speak. All right. Problem B, raising a number in scientific notation to a power. This comes from lesson 7.3, problem number 5 in the textbook. So we want to look at, we've got the expression 1/2 mv squared gives the kinetic energy in joules of an object with a mass m of m kilograms traveling at a speed of v meters per second. What is the kinetic energy of the Voyager 1 space probe if it has a mass of 7.219 times 10 to the second power and a velocity of 1.726 times 10 to the fourth? So let's start just by writing each of our pieces. We start off with 1/2 times our mass, which is 7.219 times 10 to the second. And that's in kilograms. And we are multiplying it by our velocity squared. Our velocity is 1.726 times 10 to the fourth meters per second squared. Okay, so now we type in all of this into our calculators. So we have 1/2 0.5 times 7.219 times 10 to the second times, I'm going to put this in parentheses, 1.726 EE4, and we want to raise that to the second power because our velocity is being squared. When we hit enter, we get a whole long number. So when we get big, ugly numbers like this, we're just going to round them off. So I see 1.075. So I'm going to start with that. 1.075 times 10 to the 11th power. And we said kinetic energy is being measured in joules. So it is joules. 1.075 times 10 to the 11th joules. Now, just a quick aside on the picture. This is a copy of the two records that are on Voyager 1 and Voyager 2 space probes. The one side has sounds of the Earth, so they have people saying greetings in various languages, as well as sounds of nature. And on the other side are astronomical descriptions of where to find Earth in relation to other things in the universe. As well as the fact that we talk about mathematics and that hydrogen is the most common atom. So we use some different codes there. So those are actually gold-plated records on the sides of both of the space probes that should be able to be played for thousands and thousands of years. So that would be kind of cool if anybody ever finds these. All right. Next up, we have the expression 1/2 mv squared gives the kinetic energy in joules of an object with a mass, same as the last one. All right, now, this time we're talking about the SR-71 Blackbird, which is, as of right now, still the current fastest air-breathing aircraft ever. And it was flown, it started flying in the 1970s. It was declassified in the 90s, and it is currently retired. But we can still figure out what its kinetic energy was. So if it had a maximum mass of 7.711 times 10 to the 4th kilograms and a maximum velocity of 9.84 times 10 to the 2nd meters per second, we use our equation 1/2 times the mass. So we have 7.711 times 10 to the 4th. And then we multiply that by our velocity, 9.84 times 10 to the 2nd power squared. So now we need to just type all of that into our calculator. 0.5 times 7.711 times 10 to the 4th times, we're going to put in parentheses, 9.84 times 10 to the 2nd, and we're going to square that, and we get 3.733 times 10 to the 11th power. 3.733 times 10 to the 11th power. Okay? All right. Problem C, dividing numbers in scientific notation. This comes from section 7.4, problem number 2 in our textbook. And I am looking at the population density. Population density is the number of people per unit area. During 1 year, the population of Angola was 1.21 times 10 to the 7th people. The area of Angola is 4.81 times 10 to the 5th square miles. What was the population density of Angola for that year? So first off, Angola is this country right here in Africa. So we want to know, it is the number of people per unit area. So when we see that word per, we're dividing. So number of people, so the population was 1.21 times 10 to the 7th over the area, 4.81 times 10 to the 5th, and we can calculate that. 1.21 times 10 to the 7th divided by 4.81 times 10 to the 5th, and that's going to give us 25.16. So that's 25.16 people per square mile. Okay, so we're going to just write decimals on these because, that makes sense. All right. During 1 year, Honduras had a population of 7.33 times 10 to the 6th people. The area of Honduras is 4.33 times 10 to the 4th square miles. What was the population density of Honduras for that year? Now, first off, Honduras is this country right here in Central America. Very cool country. There's an island there on the coast called Roatan, and it has a nature park on it. And so when my family was there 1 year, there's this area of it called Monkey Town, where they have monkeys running around. So I have a picture of myself with a monkey sitting on my shoulder. Random picture. All right. So we put our population on top, our area on the bottom to find population density, and now we just need to type it into our calculator. So 7.33 times 10 to the 6th divided by 4.33 times 10 to the 4th. And it is approximately 169.28 people per square mile. Okay. All right. Moving on to problem D, which isn't quite in our textbook, but these kind of problems I think are kind of fun. Mrs. Zirzo doesn't. She's wrong. So, we've got the mole is a unit of measure that you're going to learn about in chemistry. 1 mole is equal to 6.02 times 10 to the 23rd atoms in a substance. If we have 1.8 times 10 to the 24th atoms of aluminum, how many moles do we have? We want to write our answer in scientific notation. So we've got 1.8 times 10 to the 24th atoms of aluminum. Sorry, should be lowercase l. And we want to know how many moles there are. So if I know a ratio, oh, that's chapter 2 again. Yay, lesson 2.5, Mr. Bowen's favorite lesson. All right, so we're going to do some conversions. So we have 1 mole of aluminum is 6.02 times 10 to the 23rd atoms of aluminum. Yay, conversions again. Mr. Bowen's happy. Okay, so we look at our conversions. We've got atoms of aluminum canceling out. We're left with moles of aluminum, which is what we want to know. So now we just need to do the math. So 1.84 times 10 to the 24th divided by 6.02 times 10 to the 23rd, and we get, sorry, it was 1.8, not 1.84. 1.8 times 10 to the 24th divided by 6.02 times 10 to the 23rd, we get 2.99. 2.99. Bottom one, not the top one. All right, so that is 2.99 moles of aluminum. Now, chemists are lazy, and they abbreviated mole, which was already a 4-letter word, to 3 letters by just dropping the E. It is what it is. All right, so that's our answer for question A. What do you get when you cut an avocado into 6 times 10 to the 23rd pieces? Guacamole. Yeah, yeah, great, love it. You can stop rolling your eyes now. 1 mole is equal to 6.02 times 10 to the 23rd atoms in a substance. If there are 0.5 moles of sulfur in a sample, how many atoms are there in the sample? Write your answer in scientific notation. So I know I have 0.5 moles of sulfur, so that's 0.5 moles of sulfur. And I want to go into atoms, so I know that 1 mole is 6.02 times 10 to the 23rd atoms. So I need moles to be in the denominator to cancel. 1 mole of sulfur is down there. We're going to have 6.02 times 10 to the 23rd atoms of sulfur. Okay, so again, when we do our canceling, moles of sulfur cancels out, and we're left with atoms of sulfur. And now we just need to multiply. 0.5 times 6.02 times 10 to the 23rd. And we get 3.01 times 10 to the 23rd. So there are 3.01 times 10 to the 23rd atoms of sulfur. All right, so let's move away from the chemistry world a bit to the physics world. The speed of light is 3 times 10 to the 8th meters per second. If the sun is 1.5 times 10 to the 11th meters from Earth, how many seconds does it take for light to reach the Earth? And we want to write this in scientific notation. All right, so we are going to start off with, well, let's find our information. 1.5 times 10 to the 11th meters from Earth, and speed of light is 3 times 10 to the 8th. So if I know that I am 1.5 times 10 to the 11th meters from the sun, and I know that this is the speed of light in meters per second, so in 1 second, light goes 3 times 10 to the 8th meters. Well, now if we just do our canceling, meters cancel. We're left with seconds, which is what we want. How many seconds does it take? Now we just need to do the calculation. So that is 1.5 times 10 to the 11th power divided by 3 times 10 to the 8th power, and it is 5 times 10 to the second. Okay, 5 times 10 to the second seconds, or about 500 seconds, which is just a little bit over 8 minutes if you were to convert that over. Okay. Last question. The nearest star outside of our solar system is Proxima Centauri, which is 4.22 light years from Earth. If 1 light year is 9.4607 times 10 to the 12th kilometers, what is the average distance from Earth to Proxima Centauri? Write your answer in scientific notation. All right, so we start off with, we know that we are 4.22 light years from Proxima Centauri. And I know that 1 light year is, well, it's the distance light travels in a year, and it is right there, 9.4607 times 10 to the 12th kilometers. Okay, so over the course of 1 year, light will travel that far. All right, so now we need to do our calculation. So we have 4.22, the number of light years, times distance that light travels in a year, 9.4607 times 10 to the 12th power. Hit enter, and we get 3.99 times 10 to the 13th. We have 3.99 times 10 to the 13th. All right, and we're left with kilometers. All right, so that's approximately how far it is. 3.99 or 399 followed by 11 zeros. That is how many kilometers away the closest star outside of our solar system is to the Earth. Okay, so today make sure you guys fill out your level of understanding. Write down any questions you may have or any confusions that may have come up while we did this lesson. And lastly, write down your summary of what you learned today. Have a great night, and I will see you in class.